That's been
It's been almost 3 months.
yes, 3 months
Um,
almost.
I'm sure you must have been busy with other stuff as well.
Yeah.
Yeah. Also, hello, Joffrey. Good to see you.
Oh, hello.
Um, Hi, I'm all right. Today I was just finishing up my dissertation for my bachelor's program. So just finished it today.
Nice.
Sent it for printing and binding and whatever. Yeah,
Good, good.
nothing much else. I'm just remember I told you that my paper came back for they asked for revisions. So I was doing
Mm-hmm.
revisions right now actually. Adding
Good, good, good.
Yeah, I think one way to handle their revisions is that just add footnotes. Whatever they're asking, add it in a footnote.
I see. Nice.
Hello,
Okay.
hello,
Hello, hello,
Shakzod.
hello.
How do I refer to you?
Sorry, can you repeat?
What do I call you? What's your name?
It is Shazwat, as you see, but you can call me Shaha. It's much simpler and easier to pronounce. Shaha.
Okay.
Yeah, Shaha. That's cool.
No, if Shah is your name, then I can use that as long as I'm pronouncing it all right.
Yeah, you're doing well.
Okay. Hello, Kai. Is it Kai?
Yeah.
Hello,
Okay.
Kai.
Okay, so Divya, I finished. I started the first chapter and I finished. I think 15 pages. So far, I think the basics are clear to me. How the book is building up. But I'm
Okay.
ready. I'm ready to proceed.
Okay. Great. Yep. Let me just give me a minute. I will get some water and be ready, and then we can start reviewing the first chapter. So again, Kai and Shakzod. So what I plan to do today is review everything that we've seen. I think you guys should already be on board with that. If there are any proofs or not, like we'll just clear that up. And I wanted to hear from you too. Do you want to go on this, long church roser proving thing, or should we just go to chapter two? I want to do church roser, but then I can just do it alone if both of you are not interested in that.
I'm okay doing Church Roser. I was reviewing this book today and remembering all
Mm-hmm.
these concepts. So, yeah,
Mm-hmm.
I can do Church Roser. I can talk about Church Roser, or we can just straight go to the second chapter. I'm okay with both decisions.
Okay, Kai, what about you?
So hello, first of all. If it's not gonna take some like 1.5 hour, well, I don't mind it. But I tried it myself in Lean. Um,
Mm-hmm.
um, it has left some really bad impressions on me. It's really hard. So if it's easier in paper, I don't mind it.
How long do you think it will take to cover Church Rosal, Divya?
Um, say it again. Sorry.
How long do you think it will take to cover Church Rosal?
Yeah, church roser will at least take 2 sessions, at least.
Mhm.
So that in like almost 3 hours, other than right and all. So church roser is a big theorem. Church roser is almost 5 pages long. The shortest one is 5 pages long. It's a long proof. Um, so yeah, it will take long, but I think it is worth doing it. But again, that is me personally. If people do not agree on it, just move.
Does the entirety of proof facilitate understanding the everything in the first chapter of the book, or is it that we can pick and choose what the elements which we require for the first chapter?
So I read the second chapter, and Church-Russell's theorem is useful there too. It holds for simplified lambda calculus too. So that too.
Mm-hmm. I have some connection issues, I think. Oh no, it's okay. It's okay. In a minute.
Yeah, we can hear you.
Okay.
I think
Yeah,
Divya
I
is
just
having
got
some problems.
disconnected for a while. Yeah. Can you hear me now?
Yeah,
Mhm.
we can.
Yeah, I was saying, what did Josephine say? Did she say that does Church Roser have things related to the first chapter? It does have things related to the first chapter. It has some more clever techniques of proof that are interesting. But certainly it have all the things related to reduction, substitution that are in the first chapter. Yeah.
So
I see.
when it comes to me, I mean, I was reviewing the first chapter today, and I realized that some lemmas, namely 171, doesn't make sense. I was trying to provide counter examples here. So yeah, we have to, I think, go
Okay.
through that once more too.
Sure.
173?
Sure.
Modulo alpha equivalence, 171.
Okay. Yep. Just give me a minute. I will be ready.
Mm-hmm.
Shafil, do you have any of these?
What exactly? I'm trying to understand Church-Roser. It is kinda obvious to me, but I feel that there is some tricks inside hidden, so therefore I don't know. I'm just following you in reasoning for now. Also, can you hear me? It's a lot of interruptions. I think
Yeah, I can
it's
hear you.
issues with my internet or something else.
It is.
Yeah,
It
I
is
can
my
perfectly hear you.
internet.
That's cool. So yeah.
Yeah. Yeah, I understand. What I'm saying is, Church Roser is easy to understand but difficult to prove. It's one of those theorems.
Mhm. I mean, it is
So
easy to
that's
follow
okay.
up when there is only N1 and N2 and N3 with 3 examples, but
Right.
when you have
Right.
I don't know, the thousands of bit reductions, and there is tricky to
Yeah.
imagine.
Yeah. So okay.
Also, the thing about these
we
paper-based
go
proofs,
ahead.
sorry for interrupting. So the thing about these paper-based proof is that, I mean, while proving the fixed point theorem, I realized that sometimes I think, I don't know why, but maybe author takes some things for obvious. For example, in the fixed
Yep.
point theorem, it says that we take for arbitrary L. So I'll write one moment. So basically, he takes for arbitrary L and M, and then just proves that L application of M to L is better equal to the M itself. However, while proving it, I realized that the X, so it defines M as a combinator, as you can see. So there should be a constraint that x is not a free variable in L. It's not specified anywhere, and that's what got me stuck for a while. After adding that constraint, everything worked, and the theorem was proven. So yeah, there's
that
this
is
kind
one
of
of the
things
things.
too.
Yeah, so that is kind of our job. Whenever we are doing is the books usually have very summarized proofs, and you have to fill in the details and have it make sense. Yeah, that's kind of the exercise. But I'm glad you were doing the fixed point theorem, right?
Which one?
Fixed point, it's 1
Yeah.
point. Which one it
Yeah,
was?
fixed point. Yeah,
1.10.
110.
Yeah, 110.
1.10.
Yeah. Okay, so should we start with what Kai said, 1.7.1, right?
Yeah, okay, fine.
Okay, all right. Let's make the what board were we using? The online board. I forgot.
You can share your screen if you're okay to.
Yeah, let me try that.
Yeah. So we can all follow the one page.
Yeah.
Or if you guys want, I can share my screen and demonstrate what is the problem that I'm having. I think DV is disconnected.
Okay, no problem.
Let's wait until he reconnects.
Mm-hmm. I also have a physical printed book, so I'm following the book and forgot to scroll the book on the computer.
Mm. All right, let me just share my screen
Mm-hmm.
for now.
Okay.
All right. So, can everyone see
Yeah.
my screen? All right. So the thing is, we have until DV reconnect. So it is recorded. So, anyways, so
Mm-hmm.
if he joins, I can re-explain it again, clarity. So we have a modulo alpha equal. Basically, by the book, it states that if we have M1, which is alpha equal to N1,
Mm-hmm.
and equal to N2, then also these cases are true. So that's the first case, application of M1. So application of N1 N1 to M is alpha equivalent to the application of N2 to M2. The problem is, so M2 and N2 are alpha equivalent. They are related by alpha equivalence. And
Mhm.
M2 and N2 are also related by alpha equivalence. However, these both statements are not related. I mean, M2 is not related to either one of them, or N2 is. How can we state that it is alpha equivalent? The applications are alpha equivalent. So let's take an example. So what we're saying to what we're trying to say is we have an ID X and ID Y. Let's just arbitrary. So they are alpha equivalent. I mean, I was proving it, but I mean, it's really getting out of hand. So I just, for now, let's think about it. So, and we have, for example, delta X and delta Y, which are also alpha equivalent. So the thing is, how is the application? So application, here's the application, and here's the application of delta X to delta Y. So our theorem states that, again, M is equal to alpha equal to P and N is alpha equal to Q. So IDX is alpha equal to IDY, we have H and P, and delta X is alpha equal to delta Y. And it says that the application of IDY to IDX is alpha equivalent to application of delta Y to delta X. How on earth is it alpha equivalent? I mean, if we evaluate the application of both of them, they're not alpha equivalent at all. So I think
Okay.
you're here.
So yeah, I'm back. So you're saying how both of them are alpha equivalent? Yeah, I'm not sure if I understood because I joined a bit late.
Doesn't make sense. I can re-explain it. So basically, what I'm trying to say is that, so we have relation between M1 and N1, and we have relation between
Yes.
M2 and N1 and N2, but we don't have
Yes.
any connection between any of them. So I mean, we only have N
Yeah.
equals, but it doesn't mean anything. How on earth can we state that application of this to this is alpha equivalent of this to this?
Yeah,
take this example.
That's from the definition of alpha equivalence, though, right? If you apply things, alpha equivalence remains. So even if it wasn't M1 or N2 or anything, so for example, let's say that A is alpha equivalent to B, then I can apply some lambda term to A and to B, and those applications will remain alpha equivalent. So alpha equivalence respects application. That's from the definition of alpha equivalence. If we go back, let me see.
Yes. So, so here's the definition of alpha equivalence. So we have cases of compatibility of left application, right application. So
yes,
left, and compatibility of abstraction. I mean, this can be arbitrary. They cannot be structurally. They can be structurally not the same. And I mean, if we were talking about beta equivalence,
so you're asking how M1 and M2 came there?
Yeah, how these and these can be related at all. I mean, these can be arbitrary, as I demonstrated here.
Yes.
Identity.
Yes.
And delta.
Yes.
They're arbitrary. They're not
Yes.
related at all. And if we evaluate it and see the results, they're not alpha equivalent at all.
Okay. I understand what you're trying to say. Let's see.
Even by the definition of alpha equivalence, there's no such rule that can relate arbitrary terms. I mean, left equivalence, if we have an alpha equivalence, and so the main constructor of alpha equivalence is renaming. Others are just properties. I mean, all of them require present alpha equivalence to be. The only thing only way to build an alpha equivalence is by renaming, and renaming is defined as this. So, but the thing is, just doesn't make any sense. We cannot, you know, I
Okay.
mean, if we
Let's see.
rename it, it does make sense.
Okay. Yeah. Can you see my screen?
Hold on a moment.
Yeah.
Okay. Okay. You see what I'm drawing, right? Let me go. Yep.
Yep.
Okay. So we start from the definition of alpha equivalence or alpha conversion, right? Let me just copy paste it from page number 10 of the book. I will just copy and paste it. Yeah. So we have to show that, what is it? 1.7.1, that if M1 is alpha equivalent to N1 and M2 is alpha equivalent to N2, then M1, N1, M1 applied to N1 is also alpha equivalent to M2 applied to N2, right? Okay. My brush, I don't know why it was like this. Anyways. So where we start from is that, okay, if M1 is alpha equivalent to N1, then by the compatibility law, that if two things are alpha equivalent, then you can apply the same thing across each side, whether it is left or right, and the relation remains, right? So
Yes,
we
right.
can have, right, so we can have M1, N1, alpha equivalent to N1 applied to N1. Do we
Yes,
agree?
it does make sense. Yeah,
Yeah.
it does make sense.
Right. Now that is given. Then we start again from M2 alpha equivalent to N2, and then we can say that M2 applied to N2 is alpha equivalent to N2 applied to N2. We agree.
Yes.
Okay. Now we know also that N1 applied to N1 is reflexive, right? Sorry, it's symmetric in the sense that it goes both ways. N1 applied to the same thing, like you reverse the order, you get the same thing, right?
Yes, it can be swapped. They can be swapped.
They can be swapped, right? And because they can be swapped, what we can do here is, let me scroll a bit further. So what we have to do is basically we have to show that N1, N1, N2, N2 are somehow related. They have alpha equivalence there. And to do that, what I will do is, just give me a second. If we start with M2, N2, okay, so another thing I think we can use is, can we say that M1, M2 is alpha equivalent to N1, N2?
Yeah, that's
Can
the problem. If we had that relation, we could just apply that, and by compatibility, we could build it. But for example, if M1 was alpha equivalent to M2, N1 was alpha equivalent to N2, and without the present relation, with just these relations, we could construct by the compatibility. I think maybe I'm wrong, but what I was thinking is that the book, for example, for maybe contains a typo or something, or I don't know. So yeah, if that was the case, so if we could, where is the screen? I'll tab to the wrong. Yeah, I can see it now. So if we could, say that M1 was alpha equivalent to M2 and N1 alpha equivalent to N2, we could build it, I think.
Mhm.
I have a suggestion.
Mhm.
In the start
Mhm.
of the book, we have a link to their website. So hopefully
Mhm.
we can find something there. Wait a minute. Well,
Yeah, if there was an
The errata
errata,
or
they
something.
will link to it. Yeah, but it's highly unlikely that there is an errata.
So there is the link to their website. Uh-huh.
Mhm.
And
Yeah.
Do we
Yeah.
can we
There's
do
a
something?
errata.
Okay.
So it says that instead of M1 alpha equivalent to N1 and M2 to N2, read M1 to M2 and N1 to N2. I can share the screenshot.
Okay.
yeah, let's share a
Okay.
screenshot,
Then we have to
please.
be very. Then we have to be
Yeah.
very careful with this.
Yeah, I mean, I was thinking, and it doesn't make any sense. I'm trying to prove it. It's not coming together, and I was,
Okay then. Thanks for the link. There's a whole errata, right?
yeah, 52 pages long errata.
Oh Christ, they made a lot of errors. This does not make it easy. This does not make it easy. Can you also share the PDF of the errata? Let me see.
Yes.
Okay, thank you. That's good. Yeah, we have to keep this in mind while we do this. Otherwise, it is very easy to get lost. Yeah.
Yeah.
Okay, then if M1 is alpha equivalent to M2 and N1 is alpha equivalent. Sorry?
I was gonna ask which text is the screenshot from?
The screenshot is from the errata. We just linked to the PDF.
Thanks.
Yeah. But yeah, if the errata is obviously right, so M1 alpha equivalent to M2, N1 alpha equivalent to N2, that makes sense, right? Yeah, if we have that, then we can just do this. We all agree?
Yeah. Because by compatibility, they both hold. So the thing is,
Yeah.
I discovered it like 25 minutes ago. And the thing about this is, I rehearsed the first chapter for like 4 to 5 times during these half a year, during 6 months. So basically, the thing I was just not paying attention to it, and I didn't even define it up until 25 minutes ago, because I thought it is all given as a compatibility rule, as an abstraction rule, and I just ignored it.
Right.
And now I discover it, and we can ignore the first and second rules because they are already given as a compatibility.
Yeah.
But for the sake of clarity, we can define them as a lemma. And the third one is interesting. The third one should be defined too, because I read the first and second ones, I just ignored it and didn't read the third one. The third one I think is important too, so we need to define it. So
Okay,
that's
let's
why
do third one.
yeah, I already. It's not that necessary. I just saying that to define it in lean. So
I see.
yeah, not now. So the thing is, I ignored some other definitions too. For example, up until 25 minutes ago, I ignored other definition, which is alpha variant, and it's just an abbreviation for alpha equivalence.
It is.
So
It is.
yeah. So I just because there are a lot of abbreviations and all of the stuff, I just kept ignoring and kept ignoring. Yeah. So, yeah.
It's understandable. It's understandable. Okay, so should we do the third statement, or does it make sense that if you replace x with n1 and m1 and x with n2 and m2, then they are alpha equivalents? It like you can use 1, 2, and the definition to prove it, I think.
Yeah, it just makes sense because I mean, if they are alpha equivalent, they're structurally the same. So if they are
Yes,
structurally the same, they evaluate to the same value.
yes, yes, yes. Yeah. I will just put a note on this to not forget myself and make myself mad. Yeah. Okay.
Okay.
So
Isn't there a newer edition of this book with errors rectified?
Good question.
I
We need
don't
to
think
check
so.
that.
I don't think so. I think when I got it was, I think it was, when was this? This was 2014. Yeah, I'm not sure if there's any.
Yeah, mine physical also from 2014.
So yeah, the most recent edition is 2014, so there is no more recent version. So we had to deal with the errata.
Yep. Okay. Anyway, so that makes sense. There's the errata. Is there any other errata for first chapter? Maybe we should check it. Let's see.
Yeah, that's a good choice. So it says that page definition.
Mhm.
Yeah. So the definition 1.6.1. So it is the definition of substitution.
Substitution. Okay.
Yeah, I kind of already. Yeah, so we should add z that is not equal to x there.
Z is not equal to x. Yes, Z cannot be x. Yes.
Yeah.
Yeah. If Z were x, then it will also be reduced.
Yeah, but the thing about this z that is not in free variables of n, and so
Exactly.
z is not z is not equal to x implies that z was generated, and I mean with my definition that with substitution that has a gen sim, it generates a new symbol. It's almost impossible to do any proofs because first of all it has a loop and a state monad. So yeah, when you try to do proofs, you will get an infinite indirect. So state tmap, state tpure, bind, seek, all these applicatives, and so on and so forth. So yeah, I define substitution without the generation part. So I just, if y is in free variable of n, I just leave it alone and just return it without generating and all doing stuff. If you generated proofs are nearly impossible. And other errata, so they're not. So there are in examples, and they're not that relevant.
Okay.
I think
Okay.
page 59.
Yeah,
That's already on the second chapter, if I'm not mistaken.
Yeah, from next chapter onwards, we'll keep the errata in mind as we do the chapter. Okay.
Yeah, there are on other chapters, so no relevant errors on first chapter other.
Okay. Okay. Anything else other than Church-Rother from this chapter that we should discuss? confluence was yeah,
I think
confluence
there
needs
is
structure.
none.
Yeah.
Are we including fixed point theorem?
Fixed point theorem, we could do it. I think we could do a fixed point theorem without Church-Rosser. Yeah.
Mhm.
Yeah, it's pretty easy to do so. Just it's not given in errata. I searched it, but we should keep in mind that x should not be a free variable in L during this proof. The proof is really easy, like 3 lines and that's it.
Yeah, it should not be that.
Even in
difficult.
lean, it's like 6 lines.
Okay, let's discuss this because there's something related to the Y Combinator as well. So let's discuss this and then maybe think about what we do with the Church-Rosser monster. Okay. So this is theorem 1.10.1. It states that for all lambdas in the big lambda, so this is a lambda term, there is another lambda term m such that L, m applied to L is beta equivalent to n. That's the fixed point. So fixed point theorem are actually very common in mathematics. Fixed points basically something gets applied to a function that keeps it the same thing. So f of x equals to x. That's usually it's actually something also in topology. And it says that there is some x for the function f such that f of x equals to x. And you just have to prove that indeed that is possible. So
we can think of it as an identity, not in the terms of values, but identity in terms of functions, kind of.
yes.
I have
like
yeah,
the
I had
identity
some same idea about identities,
Mhm.
but
Yeah.
I read somewhere that so they show the big L. It was Y Combinator, and also it called Mockingbird, if I'm not mistaken. Mockingbird Combinator. A minute. Yeah, Mockingbird Combinator, the function which is applied to itself, and non-terminable. If I'm right.
Yes. Yeah, this is the way to do loops in a purely functional language or loops in lambda calculus. You cannot have conditionals that if this is true, then this is true, then you do. You have this recursive loop that goes on. This is one of the reasons why it used to be the famously people used to say that functional languages just heat up your CPU because there's no termination. It keeps on doing the same thing. Yeah. But that's the idea, and the proof is pretty simple. You just take an L and you define M to be like this. You have the lambda x dot L applied to the application x of x, and then that whole other term is applied to the same thing itself. See?
Yeah, the
And
thing
now you
X. Okay.
Yeah, and then you try to do beta reduction to that. So when you try to do beta reduction to this whole expression, well, I think you can do from inside or outside, doesn't matter. But I think here they're doing it from inside. Yeah, they're first clearing this. Should we go into this? Do you want me to like elaborate on the whole reduction?
Um, overall, it's clear. You can say to me.
Okay.
If you
Okay.
want, it's easier in lean because it does it automatically. If it's really necessary to demonstrate, I can just really do it in lean. We can go back if you want.
Yeah, sure. You can explain. It'll be nice.
So let me share my screen. Continue.
Yeah. This endless
So,
screen was a Y Combinator.
Yeah,
Yes.
yeah, exactly. So let's I have defined a lambda. So basically, let's define fixed point as let's not do that, but I mean let's define m. We have it already here. So L, instead of L, for example, take the identity, for example. It's
Right.
it's the easiest thing you can do. Otherwise, with the combinators, we're just gonna sit there all day. So basically, let's say MM and UU. Basically, X, let's say not X, it should be Y because identity already contains X. No, it's not free variable. We can use X. So basically, and if let's evaluate M, let's say F, let's say it as F. Right, so let's evaluate F to string. We have this thing, so we have identity
Right.
and
Right.
all this.
This is
If
exactly what we had in the proof.
Yeah. So if we better reduce it once, so the identity is now it goes from inside to the outside.
Right.
So yeah, and it is equal. It's literally equal to putting I. So the I. Let's hypothetically say that I applied to you. It's going to be what F itself. So basically,
Yes.
yeah, yeah.
It's just a complicated way of saying F. Yeah.
Yeah. So let's say IF is going to be equal to F. So basically, works like this. And if you
Yes.
try to do that, or it can be not just even do it, not this, but just a variable z, let's say. It's even easier than yes, not identity, but yeah. So here z goes to the outside. So, and if we keep doing that,
Right.
it's going to FI, and that's it. So basically, yeah, it evaluates.
Basically, the proof of the fixed point theorem is to show that the identity function, the identity combinator, exists.
Yeah, basically that's the whole point. That's how it reduces. And there's also, if you can read it afterwards.
You've already done the
it's
S and K. Have you gone into the S and K, the whole ski combinators and the mess?
There was a book that the authors recommended, Lambda Calculus and Combinators, if I'm not mistaken. But no, I did not go that deep yet. So I just defined them here.
Yeah.
Yeah, I read the introduction on that book. Didn't go that far.
Yeah, you can do a lot. I remember there was this language that was a dialect of fourth called Joy, and Joy is built entirely out of these three combinators, S, K, and I.
Yeah,
It's pretty interesting what you can do with it.
Turing complete, yeah. SKI.
Yeah, they're Turing complete.
yeah, I'm gonna stop sharing my screen now.
Okay, so we should continue with the chapter. Yeah, that is a fixed point combinator. The Y combinator is one type of fixed point combinator that allows us to do great things in functional programming.
And also the interesting fact is that anti-calculus is too powerful. That's why we can prove it that easily
You
because it
cutting
allows
out.
self-application. Can you guys hear me right now?
Yeah, we're hearing.
So the interesting thing about fixed point theorem in anti-lambda calculus is that, I mean, I realized that anti-lambda calculus is too powerful and therefore it allows application. So application of x to x.
Yes.
When it comes
Yes.
to simply tap lambda calculus, the fixed point doesn't hold there, at least this
Right.
definition.
Yeah, in simply type calculus, you have to do more work to make that happen. Okay.
So yeah, that is all I have to
These
say.
two.
For the
Should
entirety, I
we?
think.
Okay. Okay. Am I audible? Am I cutting out?
No, we can
you're
hear.
audible.
Yeah. Just give me a second. Let me rejoin. I think there's something on my phone. Okay. Yep. Can you see my screen, by the way?
No, screen disappeared.
Not yet.
Okay.
It was shared before a moment while.
Okay, so I was saying is that the examples in the chapter for the fixed point combinator have two things. One is related to this, what is it, lambda term such that mx is beta equivalent to x mx. That one is easy, but the other one where they say that you can have natural numbers in untimed lambda calculus. Obviously, this is using Church numerals. But what I was thinking is, should we try to do it?
Excuse me, if you're showing us a share screen, not
Yes.
seeing the screen.
Yes.
We're not
Yes.
seeing the screen, yeah.
So this is the example 2 that they have. How to have natural numbers in untyped lambda calculus. I think they have exercises related to this as well. Do you think it's a good idea to do this? I think we could do this. We could do this in any language, to be honest. You just need to first do untyped lambda calculus evaluator, which we did in the with Kai. We did in the IFP FCP competition. We basically did the untyped lambda calculus, right?
Yeah.
Yeah. So we could do that and then have numbers in them. That will be a good thing to do, or we could do it in lean together. That will also be a good idea.
I don't really know.
But I guess conceptually you understand how we can use fixed point theorem to numbers, right?
You mean a successor, predecessor kind of thing?
No. Yeah, so this is the whole idea behind Church numerals. And this is how numbers are done in pure functional languages. So instead of like in usual ways of understanding numbers, you have like, one set, and then you do this bijective function that relates it to another ordinal set and stuff like that. But there's a much more cleaner way to understand numbers, and it starts from the null set. So we have the null set, which is the set with nothing. You can see my screen.
No.
No.
You do not see my screen. Wait. Can you see it now?
Yes. Yeah.
Yes.
Yes. So we first start with a null set. So the null set is the set with nothing in it, right? And then we say that for number 1, it will be the set with one null set. So see, it was the same. It was the same thing that Kai was doing of applying I again and again to F. So we apply here phi, or the null set, acts as the identity function, identity combinator, so to say. So 1 is this, 2 is this, and 3 is this.
It is like, sorry to interrupting you. It is not like a successor thing, which is deeply nested.
Yeah.
It's more like constant nil, like in Haskell.
Yes, exactly. It's a recursive way to understand numbers, because what you're doing is you're first starting with null set, and then you're recursively using this definition in another definition of 1, and then you're using this definition and this definition. See? So you can construct numbers just by repeatedly applying the identity function again and again and again, and the number of times you apply, that's basically your numbers. So this was a constructive way to come with numbers compared to the classical way, which is not constructive. So we can do this in Lean, and it will be easy. The difficult part will be these things, the multiplication, addition, and the successor function. Otherwise, it should be easy.
So making, it is hard to implement successor, you mean? Yeah.
Not totally hard, but it is.
It is
because,
non-trivial in comparison.
Yeah.
Okay, so for any number n, then what is the definition of that number n in this constructive paradigm?
So n will be the identity function applied n times. You see, so 1 is the identity function applied 1 time, and then you apply 2, then apply 3. So identity function to the power of n is n.
Can you explain the case for 2 again?
Yeah, so again, so 2 is, so you understand 1, right? 1 is just one null set in it.
Yeah.
Yeah. So what you do is you try to, let me do this here. View phi is just your usual null set. 1 is 1, and 2 is basically the same thing applied twice.
But I'm thinking if it's recursive, so why isn't so in the two set in the set for the number two, why don't we have a null set within the null set which is part of this set?
Oh, we do. Okay, I didn't draw the. I didn't draw it. I see. It is like that. So you
Ah,
have.
yeah, I was confused
Yeah,
and thinking about how to do that.
okay. Yeah.
Yeah.
No. I draw it wrong. This is.
Okay.
This is,
Now, yeah. Now it feels right. Yeah.
yeah. This is how we do it. So for two, you will have the whole thing. You
Yes.
will have 1, 2, 3. Yes. Getting lost in brackets. Usual day for Lisper.
Yeah. You should.
And then we
You should.
will.
You should put an asterisk for illustrative purposes, not to scale.
Yeah, so this is 2, this is 2, this is 1.
Yeah.
And
Okay.
yeah, this is 0.
It's like how can I describe it? Having watching a video about my screen
Yes.
inside the screen, and it repeats. Yeah.
Yeah, exactly. So like if we had to write this like mathematically, so f of n plus 1 x is equal to f applied to f of n x and so on. So you start with just the null set, and then you apply it once, then you apply it twice, and so on. So again, now that I've written this, so the successor function is simple. The successor function is just f n plus 1 x equals to f to the n x, just once. This is so if you know n, you can apply f to it twice, and then you get fn plus 1. So f to the n, and then f is fn plus 1. That's the successor function.
Need to practice that with lean, for example.
Yeah, you have to do it by code. With lean, I think it's going to be a bit easier, but in any other language, you first have to construct type lambda calculus and then construct numbers and then.
Yeah, I'm very
and then
curious.
just
Can I do this using just TypeScript's type system? Because it's also Turing complete. Yeah.
You can. You just have to. I don't know how JavaScript deals with this kind of stuff, to be honest. But if it can, then you should be able to do it, I think.
I will give a shot.
So
That's cool.
I
Right.
already, so sorry for interrupting. I had already defined 0, 1 to church numerals, and I had add definition, and now I write the church to not function, so that it's going to be
Okay.
easy to see. So should I share my screen?
Okay.
Sure.
Is it
Right,
possible
so-
to charge to NAT within the range from 0 to 9? Is that explicitly defining hundreds and thousands of definition code?
Yeah, you can just have the function, right? It will be applied again and again.
So we have combinators. It's also, so as I already said before, it's available in GitHub. So by the book, 0 is defined as lambda of f. It takes f and x
to x.
and returns an x. Yeah. So 0. And basically 1 is just that's applied again and again and again to the f.
Yes.
So to make it life easier, there's also a successor. But so anyways, add is defined like this, m and fx and apply. So
this is what I meant as non-trivial. It is one line, but it is difficult to understand just by seeing it. Yeah.
So yeah, there is this function that I've written. So basically, it just converts all this mess, all this spaghetti, to understandable lean numbers. and I had to write some horrible code, reduce beta. For the future node, we have to define fully beta reduce or something until there is no read access. Basically,
So your beta reduction function doesn't reduce until the simplest form?
yeah, it reduces. It is one step beta reduction. Single step beta reduction.
It's one step. I
Yeah.
see. I see.
So when we do, for example, 0, it's 1.
Okay.
0 to 0, it's also 0. And the beauty is that there are no types. It's just functions taking arguments and so on and so forth.
Yeah.
3, some 3, 3, some 6. So yeah, we can see for example, add step by step if you guys want, but it scared me so much. It's so doesn't even fit the screen if I make it smaller. So we reduce it once, we get this, and we reduce it again, and we get this. Get this.
You
we
have
how
to
many
reduce
times?
it at
5
least.
times.
Yeah. You have to reduce it at least 5.
It's getting smaller and smaller, and in the end, we have this. And it can be reduced further if I'm not mistaken. Yeah, it cannot.
Yeah.
Further. It's just so it is the form and call sharing net, and basically there are the steps how it is getting applied, and getting the final result.
Yeah. So if you go back to the if you don't apply the church to LeanNat, if you can just delete it for now. Last application that you did. Your screen just froze for me.
Yeah, same for me. But how can you know that there is no further simplification? Better, and we can say in beta normal form.
No redex.
Every lambda term is in its simplest form. There are no access to reduce. There's no redexes. So if you look at this, if you go back and just show the lambda for 6. Yeah. So if you see this,
but define it again. So let's do 2, 1.
I mean, what if you do addition twice? I mean, add 3 to add 3. And that means you need
it's going to be invalid.
Yeah, invalid because you can do 3 plus 3, right? So 3 plus 3.
But it's going to do there is no such thing as type error in untyped.
Right.
You want to get some mess. So basically, yeah. So if we
I mean, would these 5 beta reducing functions increase if we make complex term?
Yeah.
So can we have the multi-beta? What's it called?
So this is the thing. You need a function that keeps looking for the lambda term, and if it checks that there is some redex which can be reduced, then it just does that. We did that with Kai and Haskell actually, and it is a pretty elegant function if you think about it, Kai. It did the job pretty nicely.
It looks for bound and free variables.
Yes.
If I'm correct.
Yes.
I saw this either definition, either lemma, but I can't remember where exactly. We have free and bound variables.
So basically, I think what DV want to say is that if we have this, and so the addition of 2 to 1 is equal to 3. If we look at the definition of 3, they are the same.
Yeah.
They are the
Right.
same. They are the same.
And if you look at the lambda terms, you have f 3 times. So you have lambda abstraction of f over these things. You see? So if you count the number of f's, there's actually 3 inside and
3.
another one outside. Yeah. So it's the same thing. F n plus 1 equals to f of f to the n x.
The thing I would like to know, can we possibly write the super beta reduction function, which will
So
yeah,
reduce
look
it
up.
to the full step. So there is a relation, 0 or more step beta reduction. It is already defined. So it's called, so I called it beta star. I mean, beta 0 or it was too long. And I mean, I digged some Agda and other professors in codes. They define this as a star relation. Basically 0 or there's a step. So anyways, there is a multi-step beta reduction relation, but I haven't defined the multi-step beta reduction function on the terms. There's a relation, but the term, and it's not even given in the book. I mean, we can try to do that. So reduce beta full. So basically, if we check that if M is redex, we can M reduce beta and reduce beta full.
Yeah, you
And
can
then
recursively
else.
apply it, right?
So recursively applied.
Yeah.
And otherwise, so and we have to prove termination. We're not going to do that now. So we define it as partial. So instead of reduce B, we can now do reduce B. Reduce B, reduce beta full, reduce yeah, space. Damn, we can do it like this.
So that means we have some.
Yeah. We don't need any of that, and we can, if we do church to lean net. I screwed up somewhere. Why? Why is it not working? So it reduces. I think it should be. It should be kind of a mutual recursion. Otherwise, I mean, it's going to reduce beta here.
Yeah, that's the thing. Then it will not look for it again.
Yeah, it should be mutually recursive, but
if M is redex, then reduce M, and then check again. I don't know how you. It is easier in Haskell. I will give you that.
yeah. What we can do is, I have an idea. Maybe it will work, maybe it won't. Let's do just be M neutral and reduce beta full, beta full, beta full, and or it substituted. We can, if I'm not mistaken, just do it in the just beta. And if it does, so the 3 cases are irrelevant. They're not redexes anymore. It is a redex. So we have to do is let result and if the result is regex, then we will call reduce data full on the result again.
Right. Again.
Else
Yep.
result and partial now hopefully damn it. Why we have so reduce beta for result. It should we can you know what you know what guys? We can do a while loop in
Yeah.
Okay, so
Were you-
during the session, I reached until the fixed point theorem. I will read fixed point theorem tomorrow, and if I have any questions, I'll post them in the group. But now I will.
Sure. Okay.
Thanks for having me.
Thank you
No
very
worries.
much. Thank you
See
very
you.
much.
Yeah, we're using conditionals to prove something that is recursive. This is the irony of life.
yeah
Brute force
under the hood
driven proof.
yeah, but while loop works under the hood as a as a recursive function, I think.
So it is just looking like it's just syntactic sugar.
Yes, it
Yeah,
actually
yeah. If you look at the definition, again, sim not in, so it has a mut, but it's not. It has a mutable variable which is not mutable,
Mhm.
and has a loop which is not a loop.
Okay.
It's in the state. You can use mutable if there is a state monad.
Monad. Okay.
Yeah. So while y is in free variable, we just call the gens and Benjamin check. I
Got it.
wonder if it will work here. So if while the result is a regex, is a regex, what we can do is not id but state m. So there should be not an identity because in order to get the result, let mut. Maybe it will work in ID. Who knows? Mutable works in ID. All right. Result. None. I don't know what to do. I give up.
Well, we'll look into it. Don't worry.
Yeah. I give up.
But I think it's close. It has to be some sort of recursive, clever technique you have to use. Should not
Yeah,
be more than that.
I think I have to make use of some local recursion with let rec or something, but I don't want to do that right now. It'll take a lot of time.
No
So,
worries.
yeah. Good enough.
No worries. Okay. Yeah. So okay. So chapter 1, I think we've mostly covered. So what we can do now, I think, okay. The idea that I think we have is first work on the exercises of chapter 1. Right? There's exercises. How many of them? 20 exercises. We'll try to see how many we can do. Again, it is up to you all. I will be both in pen and paper and Calc. If I understand Lean, then I might try Lean. But I have familiarity with Calc, so I will try Calc. So if you just want to do pen and paper, you can just do pen and paper as well.
Yeah,
So we do work on the exercises.
I've done it in pen and paper, but without theorem proving.
Okay.
So yeah, it's
You've done how
belief-oriented
many?
proof. The first, I guess 3 or 4 chapters. I don't
Okay.
remember.
Okay. Okay. Why don't we try to discuss the first 10 exercises next session, and
Mhm.
then other 10 exercises in the other session. I think that can be done. The first 10 exercises are pretty similar. They don't have a lot of stuff. The last 10 exercises look hard. Um, so that's one thing we need to do. Do exercises of chapter 1. And I think while we're doing exercises, we would also like keep 1 hour just to read on Church Roser. So we do 1 hour of homework discussion, the exercise discussion, and then we do 1 hour of Church Roser and see where it goes. Does it sound good?
Yeah.
Yeah.
So we agreed to do up until the next session, first 10 of the exercises,
First
and
10.
the rest of the
Yes.
10 for the further sessions.
Next session. Yeah.
Okay.
Yeah. Yeah, then we will, for the last time, be done with untyped lambda calculus and then do simply typed lambda calculus, where actually type theory comes in. For now, we don't even have types in our lives and we're still confused. Yeah, so that's that.
I think so. The untyped lambda calculus, the first chapter is, I mean, as they say, the first step is always the hardest. And I think
Yeah.
the first chapter was much harder. I already read the second chapter and half of the third chapter, and they're so easy because they say that in order to define better reduction, we just extend the definition of
Yes.
lambda calculus. Just
Yes.
some
Yes.
extension, and that's it. Otherwise,
Yes.
we already, I think, know 80% that there is to know about the machinery of these things. Other things are trivial things, I think.
Yep. Yep. You just need to respect the types and extend things nicely. Yeah. So that's that. And there's the other thing that I and Jack Joe were discussing regarding trying to implement some of this into just regular programming. Like it's open to choice if you want. I wanted to do it myself because I wanted to practice logic alongside these, let's say, let's say languages that are prone to a lot of bugs and mistakes. Right? So that's something that we can plan if we want to do it as a group, or if you think this is too much, which is obviously it is, then no pressure. Yeah.
So, I mean, I read the discussion on the group. I mean, I basically have the picture of what we need to learn and how we can use it. But if the material is certain, like we will read through this book, I think I can join after like 4th or 5th chapters of this book, I think, because separation logic. I mean, I heard a lot about horror logic too, but separation logic was really interesting to me because that's another unknown land for me.
Yeah.
So I'm interested in it too. If I have time, I don't mind learning it too.
Okay. Yeah, we do have the stuff. So if you're seeing the screen, let me see.
Sorry, can I
Yeah,
have
there's
2-minute break?
Sure. Go ahead.
Thank you.
We're just discussing. there's this book which is pretty big. It's around like 600 pages, and it discusses like everything related to program verification regarding all sorts of algorithms and structures. This is one way to start. Obviously, I don't think we can ever finish the entire book. We can only do parts of the book. And then there's the other book, which is How to Solve It by the same author, which is more introductory, and it's like 300 pages. So the material is there. It's just that the difficult part is practicing it and doing it on a daily basis. That's kind of difficult part. And
Yeah, I read.
it does require like a significant amount of basis and algorithms and data structures, because they're going to use it all the time.
Yeah, that's where I fall short.
But I think you can pull it off, to be honest, because you're already doing stuff, and I guess you're as a day job, you're a developer, right?
Yeah, I do mostly backend.
Right. So I think it should not be that hard. Should not. But again, why don't you just check the material? If you feel like you can, then we can do something. And if you don't feel like it, obviously, you don't have to bite more than you can chew.
Yeah, I'm back. So basically,
Yeah,
I have time, but the thing I require is material I should read and understand, and some
Yes.
I can say kind of exercise or things to do, because
Yes.
I'm very comfortable when I have purpose or something to do and need to learn something.
Certainly.
Yeah.
Certainly. So we have them too. We will first. So the thing is, there is no one book to do it from, right? We have to take chapters from one book and another chapter from another book. That's how we have to do it. But before even doing that, we have to first decide whether we want to do functional programming languages first or imperative programming languages first. I was planning on starting with imperative programming languages because I think reasoning about programs is something easier with functional languages. It's difficult with imperative languages, and we have imperative languages more because we just have more jobs.
I think I
So
think that the thing we discussed about in our group, that you mentioned Rust, or we have Go, C, and a lot of
Yes.
languages. I'm not still sure what exactly are we doing, and if it
so
is
what
a
we're
guideline.
doing, so what we're doing is, so first we are with one of the books. So you're looking at the screen. This is the book by R.G.
Screen is
Dromey.
not available to me. Sorry.
Yeah. So this is one of the books, R.G. Dromey, How to Solve It by Computer. Okay. So it's a book that introduces you how to prove little things about your programs, right? How to prove your algorithm and stuff like that. They do it in language like C, that is Pascal. Okay. It is not in use anymore. It is one of the good languages, but it's not in use. But the thing is, you can do everything in the book with any language that is like C, that is somewhat procedural, structured, and you can do it in Rust or Go, if we talk about the modern languages. Okay. So what I was thinking is, we take one book like this. We start first doing the exercises in Rust or Go, whatever we choose. We will choose one language and stick to it. And the idea is that just as you learn programming in these languages, you have to do data structures, you have to do algorithms in the language. We will do the same thing, but now we will do it with the additional proof writing skill, that whenever you're doing a data structure or whenever you're writing an algorithm, you have to write the proof of it alongside the algorithm. See? So what I'm trying to do with this is that while you're writing this programming language, while you're developing your day job or whatever, you can think with using these math logic tools while writing your algorithms.
Okay,
So if
can I
you
ask
practice,
a question here?
go ahead.
Sorry to interrupting.
Yeah.
You said that we need to write a proof alongside we will implement the data structure or algorithm we're thinking to.
Yeah. Yeah.
The question is how we exactly doing proof?
Yes. Okay.
Doing
Yeah.
by
Let me show you an
pen?
example.
Uh-huh.
Yeah. It will be by pen. So again, when I say proof, proof, I'm saying in a very general sense. Proof means something is correct. Okay. And you can show that something is correct in different languages. You can show it in math, you can show it in pure logic, you can show it in Lean, Coq, or you can just show it in lambda calculus if you have enough time in life. So we need to show a proof. And I think what I want to do with the project is by pen and paper, by just using math and logic. I don't want to use any extra tool like Lean or Coq, because I don't think while developing in a language like C or Rust, you have Coq and Lean available to you. You can just use mental logical tools and see the proof yourself. Just like, whenever you're doing, let's say, some sort of, bit manipulation, you use the knowledge of number theory, right? The number system, how to convert hexadecimal into binary and stuff like that. So you use mathematics like that in your programming to help it be purely correct and structured. Does that make sense?
Yes, but I'm a person who don't know how to write a proof, let's say. How can I assure that the proof I wrote by pen and paper is correct?
That's where we come, right? We will see each other's proof, we will discuss, and we will find loopholes until the proof is correct, right?
Yeah.
And we will start from scratch. I don't expect you to know how to do proofs. The book starts from scratch also. It will show you everything, how to prove a for loop, how to prove a while loop, a do loop, an if else. So for each of these structures, you have different approaches to prove them. And if you can master these little structures, every program is just made up of these little structures, right? So if you can master these things, then you can actually mentally reason how the program is correct or not.
Yeah, sure. But we say that it will be for the masses, the mass programming folks, let's say.
Yes.
How they can be sure that their proofs are correct, or we simplify everything up to some basic, let's say, constructors or guides for each specific.
Yeah, so basically the thing is, to show that a proof is correct, you need to show that every step is correct. And to show that every step is correct, you need to first understand what the step is doing. So for example, you have one subroutine that has one conditional, one if then else, one for loop, and one while loop. Okay? Now, to show that each of this is correct, first you have to master how the proof for loop or if then else is correct. So we start from scratch. We start from how to prove the for loops are correct. We do a bunch of exercises for loops. We do a bunch of exercises for if then else, and so on. When we master those things, then we can be sure that if we do these conditionals, these loops correctly, then our program is correct. See?
Okay.
So if you look at the first chapter of this How to Solve It book, it actually starts from scratch. It starts with how to proof iterations.
Excuse me, you
And
mean the Droomies book, How to Solve It by Computer, the red
yes,
book?
yes, 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 yes. It starts from scratch. It starts from how to prove iterative loops, and how then you can go on to bigger complex structures. So it will not. It will be just like any other programming sort of learning to program thing, but instead of just accepting that your for loop and while loop are correct, you just try to do it by hand. That's the only thing. You just check that whatever you're writing is correct. So that's the idea, at least. Yeah.
The other question, aren't we going to the road to invent something like theorem prover in the end?
No. I do not want to. I don't think we need to create another theorem provers. There are enough theorem provers. What I want to do is when we master these little tasks, these little subroutines, these things that make up a complex algorithm or program, when we have mastered that, when we know how to think mathematically and reason about these things, then we can apply them to complex real world examples, like making a compiler or making a web server, or making a library for machine learning or something. Use these logical techniques to create applications that are correct, that do not have bugs. You see, I don't want a theorem prover. That is a different realm. That is trying to do mathematics. I want to do mathematics to do real life programming, everyday programming. See? Because for theorem prover stuff, we already have the Lambda calculus group, right? We're doing the stuff in this book, the type theory book.
I mean,
Go ahead,
I think Shahzad's and mind problems are, you know, akin to the tale of blind man and elephant. Like, they touch an elephant, someone touched the trunk, says that it's a long animal, someone touched their leg and says that it's, and so on and so forth. I think, yeah, instead of just hearing about it a lot, I think we should give it a go, and if we like it, we can go on, and
we
if we
can
don't like it,
continue,
we
or
can
we
just
can just
abandon.
stop. Totally.
Yeah, there is the
I mean,
proof of termination section on 158.
Yeah, basically, I mean, the Hoare logic and all of them are really popular things. There are compilers like CompCert and all this stuff that it already makes use of it. So we're basically, as we are learning type theory to be able to use all the theorem provers, to be able to understand the formulation of mathematics, we'll be learning the Hoare logic, separation logic, in order to be able to use the tools on other domain, not just theory-based tools, but Hoare logic and all the other theory-based tools.
Yes. So basically, instead of always relying on a theorem prover, I want you to develop mathematical tools that you can just see, and by some, within some time, you can at least tell whether this program has correct or not. So it is good both for reviewing code and for writing code. And the thing is, it's a kind of challenge to myself, because I've been told many times that Hoare logic and all of this was great in the 70s, 80s, and 90s, but then they could not do it on large scale, and people could not build real. Like, it's the same thing that people say with Haskell, that Haskell doesn't have real world application like that. But I want to kind of disprove that it can be done, and it has been done. If you look at a lot of things in United States Department of Defense, and also Amazon, I realized yesterday, has done formal methods to make their applications better. So what I want is, why be limited to just writing programs in the old way? and why not use these techniques that have been there since a long time, and you just need to be familiar with them. So yeah, and we're already doing logic anyways. If we were not doing logic, I think it will be a big thing to do. But we're already doing logic on a type theory. You can use that and learn some new concepts and try it on a daily program. That's basically the idea. So, so here's the idea. If we can agree on a time and day, then I will just give you a rough guide through the first chapter of the book. And if you like it, if you think, you can spend some time on this, we will go, or we will stop.
Okay, but the only issue is that next week I will be in tech conference in Thailand. So yeah,
Okay.
the next week I cannot attend.
Then we can do the next of next week.
Mm-hmm.
Does that sound good to you all?
Yeah, yep. I'm okay.
Okay. So let me just get my calendar.
Yeah, let's synchronize with calendar. It would be a better option.
Yeah. So today is what, 10, right? So
Yeah.
Okay. Okay, next week you would not be available on Sunday, huh?
The whole week I will be unavailable.
Okay, the whole week you will be away. Okay. So we can do 24th November. That is next Sunday.
Yeah, fine. Perfectly.
Yeah, 24. Yeah, 24 November. We will do the type theory and formal proof one. 2 p.m. UTC.
24th.
Usual
Yeah.
time. Yeah, 24th. Yeah. Kai, are you okay with that?
TTFP on 24th
Yes.
November at the same, yeah? 2 UTC.
Same time. Yeah, 2 p.m. UTC. Yeah. For the Dromi thing, which day does it work? Saturday or I'm okay with any day, better. If we have the same time.
Let me how can I say? I can read some chapters or paragraphs of this red book, which is How to Solve It by Computer. And we can discuss it after the TTFP, basically.
Sure. Let me know. No pressure.
Yeah, I think it's good. How to solve it by computer. Okay. So I think it's legitimate. Yeah, that's cool. So for the next section, okay, have 24th November TTC, TPMHC, TTFP, and first 10 exercises. In the page 29.
Yes.
Take pages 29 up to 30. Okay. And then discuss about Church-Rosser theorem. And for how to solve it by computer. So
No.
let's think about it. Mm. Top-down design. I can read the introduction, problem-solving
Yeah.
aspect. And first, so that means I will read the first 1, 2, 3, 4, 5, 6, 7, about 7 pages up to top-down design. I think,
Okay.
yeah, that will be fine to get the basic
Okay.
understanding and have a discussion about it.
Sure. Sounds good.
From introduction up to top-down design. So,
Great. Let's pin this. Yeah.
and the book is how to solve it by computer. That's the book.
Yep.
Yeah, so far I'm not seeing that some kind of fancy thing. It's
Yeah.
just
It's
regular.
mostly typical DSA type book, just with more logic kind of stuff. That's it.
Yeah, it seems so. Yeah, it's really logic tables, P&Q, implies. They have some different sign for implication, which is clockwise rotation of or. Yeah, I mean,
Where do you see it? Can you give me page number?
yeah. I'm sending a screenshot.
This is like a subset symbol, but it is used as implication. Yeah, this is unfortunate. I like the arrow.
Yeah, me
Yeah.
too. I'm comfortable with arrow. I'm seeing that the new symbol. It's like, I don't know, exclusive or exclusive, something like that. And also, I've done some Incredible PM thing, Incredible PM, which is also good.
Nice.
Yeah. And I did it up to, I don't remember, session 4 or 5, which is
Nice.
also cool thing. I like that. And also, I understand finally the upside down and, which stands for all. Yeah,
Yes.
that's cool also. And in the end, they have simply typed lambda calculus. Yeah.
Nice. Okay, this is cool. We have a plan for next time. We did fixed point theorem and everything of chapter 1 today. So 24th we meet. The first priority, of course, is the 10 exercises, and then we see if we can do it Church-Rosser.
Yeah, I will also take some time and try finally to do it lean.
Yeah.
Hopefully. Yeah, hopefully.
Oh, then this was great. We shall meet in 2 weeks from now. Good luck with your conference. I also have to write a conference paper. now that I remember.
Actually, that's my
I
first
will-
technical conference,
Congratulations.
which is yeah about blockchains, about Ethereum builders are
Nice.
yeah.
Okay.
Hopefully see that will
Well, good luck.
end up with. Thank you very much.
Safe travels. Yeah. See you, everyone. Have a good weekend. The Sunday. I think for you it also must be nice, right?
Excuse me, repeat.
Yeah,
I said it.
almost 9.
Yeah, almost night. Yeah, it's the same for me. Yes. Have a good night.
Uh-huh.
You too.
You
Thanks
too.
for
Thank
coming.
you very much.
Bye bye.
Bye.
Bye bye.
Ne. Zo'r.
Ajoyib.
Da, ozgina
Shu
lean
Indus
qilishim
bit-
kerak. Lean'da anavi bir lean desam lean drug.
Shunaqada. Ana Sprite. Sprite'dan qilinadi.
Lean prover and
Drug.
me trying to do lean to research to lean. Yeah. Hop. Ishqib. Zo'r linkcha berdingiz. Nom nima edi? Lean ichida lean book edi adashmasam. Lean prover book. Lean prover GitHub ya. Bo'ldi, topdim. Drugs. Xo'p, mayli, men mana qilib chiqaman, qarang. Nix anavimiz bor edi-ku.
Parsermi?
Yo'q, parser emas. Yo'q, parserni alohida qilaveraman. U Okamlish Rescriptda sekin-sekin qilib o'tirman. Hozir просто konferensiya balovatarga yugurib bo'lgani uchun unaqa ko'p vaqt ajratganim yo'q. No, опять же, u ketyapti o'z xodi bilan. Hozir Rescriptda ja yemay qolsa, reason.ml qilib Okaml qilaveraman. No, в принципе, menga yoqib turibdi logikasi. Lean'da qilib ko'rmoqchiman. Hozir men bu successor narsalarni juda ko'p ko'rganman. Juda ko'p videolarda ham, juda ko'p anavda ham uchradim. O'ylaymanki, it's time qilish kerak. Bu cho'zgandan foyda yo'q. Shuning uchun olib pishtir qilmoqchiman. We'll see.
Bu yerdagi asosiy muammo Lean'ni o'zida bo'lsa ekan, oson bo'lardi, lekin o'sha untyped lambda calculus define qildik o'zimizni. Lean o'zi lambda calculus ichida yana bitta lambda calculus define qildik. Endi mana shularni beta reduce qilish, boshqa qilish.
Hammasi qo'lda o'zib chiqish kerak. Hamma narsani.
Hali aytgancha mana shu successor 01 mana shu church numerlarni biz hozircha biza define qilgan lambda calculusda define qilganmiz. Ya'ni aytmoqchi bo'lganim Lean'da define qilyapmiz. Hali bu lambda calculusimizni ichiga definition qo'shsa bo'ladi. Bu lambda D da bo'ladi. Ya'ni lambda calculus with definitions. Ya'ni Lean ichidagi calculus ichidagi definition. Definition ichida definition bo'ladi. Shunaqa. Tushunish qiyin. Aynan mana definition ichida qilish. Mana bu church to Lean nat deb yozdim. Chalib ham.
Yo'q, в принципе, men bu 10 ta qarab turibman, unaqa issue emas. Ozgina provlar bilan o'tirishim kerak, все. No, в принципе, Incredible PM qila oldim, Lean qila olaman degan narsa ushlab turibdi. В принципе, ko'ramiz. Если что, so'rab turaman. A tak, overall plan bor. Вижу путь, не вижу препятствий deganday bo'lsamiz.
No.
Bo'lmasa mouse sekin-sekin boshlayveraman. Streamchani o'chiraman-da. Bridge stream degan joydan qilishda boshladim. Stream qilishda. В принципе, нормально.
Мгм.
Да.
Так. Mayli.
Mayli, charchamang. Rahmat.
Mhm.
Bo'lsamiz. Давай charchamang. Так,
Rahmat.
video chat. Так, okay, that's fine. Sekin yopamiz. Qanaqa qilib yopaman endi mana? Oh. ha. Toggle off. How to finish an event. Yalla. Tab.